Very, very, very important lesson here. I think this is what they're going to be going after on your exam for types of questions that they're going to ask. If you don't understand what we're doing here, you're not going to understand anything else really in statistics. So please pay close attention to what's going on in this video, and then the next couple of days when we're working on this, do a good job, read carefully, and think about what you're actually doing. So we talked about mound-shaped distributions, right? Bell-shaped, mound-shaped. That's really what we're going to be going after here. That's when you have a mound shape, that's a normal distribution, okay? And normal, I mean, what does the word normal mean, right? It means like normal. It means typically what happens, okay? So like heights, weights, shoe sizes, things like that are all normally distributed. Example is like, for example, if you take 16-year-old males, right? And we say, what's the average shoe size? You might say 10. Okay, 10 is the average shoe size, whatever it is. If it is 10, then that means a majority are going to be around 10. There's not going to be a lot at size 16. There's not going to be a lot at size 4, right? There's going to be size 8, size 9, 10, 11, 12, 13, right? Shoe sizes around there. So, but if 10 is the average, or 10 and a half, right, then the majority, the biggest amount of them is going to occur at that size. So you would see that high mound, right? And then if you went 11, you'd have less. If you went size 12, you'd have less. If you went size 13, you'd have less. Size 14, less. Size 15, hardly any, right? And you'd be leveling off and have almost nothing. Size 9, the other way. Size 8, size 7, size 6, size 5, less and less and less. So the most is going to be at 10, less at 9 and 11, less at 8 and 12, less at 7 and 13. I hope you can understand what I'm doing here, okay? It kind of makes that mound shaped from the histogram, all right? Well, we could do the same thing. This example here is heights of dinosaurs, okay? A paleontologist studies prehistoric life and sometimes works with dinosaur fossils. The table below shows the distribution of heights round to the nearest inch of 660 procampsognathids, whatever that is, otherwise known as compies. The heights were determined by studying the fossil remains of the compies. And here's the data, right? So here's the heights. They range from 26 to 41 centimeters tall. Number of them, so the majority of them you can almost see it in the table. Not too many were 26 and 27. Not too many were 40 and 41. A majority of them were 33, 34, and then 32, 31. The further you get away from the average or the middle, the less and less there were. That's a normal distribution. It's not skewed, okay? It's mound-shaped. Here's the relative frequency. Now, the relative frequencies are the probabilities that they will occur at that height. So if you see 0.152, that's saying that's 15.2%, right? That's saying there's 15.2% that were 33 height, a height of 33. 0.136 means there are 13.6% that were 35 centimeters tall. Okay? So we're going to get into some questions about this. So first of all, draw a smooth curve that comes reasonably close to passing through the midpoints of the tops of the bars. So the midpoints of the tops of the bars. If I do that, midpoints of the tops of the bars. See what I'm doing here? And I want to connect those. Connect those points. Look what happens when we connect the midpoints of the tops of the bars. Oh, that was ugly. Okay. You get that mound-shaped curve. Okay, that is a normal distribution. Okay, so describe the shape of the distribution. It is mound-shaped, right? Mound-shaped. Or we could say bell-shaped. You may have heard that. Bell-shaped. All right. It's a bell curve. The mean of the distribution is 33.5. They're telling us that. And the standard deviation is 2.56. They're also telling us that. Create an interval of 1 standard deviation around the mean. 1 standard deviation around the mean. So I'm going to do that down here. Okay. I'm going to draw my own bell curve here. Okay. Now we know the mean would be in the middle of the curve, okay? And that's 33.5. If I want to go 1 standard deviation above the mean, what I'd have to do is I'd have to add the standard deviation to the mean. So I'd go 33.5 plus 2.56, and that's going to be 36.06. So, and I'm going to draw that by just, and it doesn't matter where you put it, it's just above the mean somewhere, 36.06. And then I got to go 1 below the mean because it says around the mean. Around, that's 1 on each side, okay? So 33.5 minus 2.56, that comes out to be 30.94. So if I go 1 below the mean, that's 30.94. So again, 30.94 represents 1 standard deviation, one of those deviations below the mean, and 36.06 is 1 deviation above the mean. We got to understand that. Start to understand what these numbers mean, okay? If you don't understand what they mean, you're going to be lost. Part C says from the table on the previous page, approximately how many copies, how many of these guys had a height that falls within this interval? So within the interval 30.9 whatever to 36.06. So what heights would fall in that interval? What heights would be in that interval? Well, 31 would fall in that interval, 32, 33, 34, 35, and 36. Nothing bigger than 36, nothing less than 31. All right, so we're looking for anything 31 to 36. 31 to 36. So that's going to be everything. I'm going to just circle them. 31 to 36 are the heights. Here are the number of copies that fall in that interval. So you'd have to add all those up, 60, 90, 100, 190, and 60. And I did this ahead of time just to save time. But write that out. Okay, write that out. 60 plus 90 plus 100 plus 100 plus 90 plus 60. It comes out to be 500. So there were 500 copies that had that height. All right. What does the relative frequency 0.136 mean? We already talked about that earlier in the video. It means that the relative frequency is the probability. So it's 13.6%. The probability that they would be 32 centimeters tall. 13.6 percent of the copies were 32 centimeters tall. Okay? What does the height of each bar represent? The height of each bar represents the percent of the copies. The percent of copies at each height. All right? And they want you to mark the mean and 1 deviation above and below the mean on the graph. Approximately what percent of the values are within that deviation? So you'd have to, it's easier to use a table actually, but well, let's mark it on the graph because it says to do that. So 33.5 is right here. This is 33.5. And then 1 deviation above, you got to add 2.6. So we said that was 36 or so, 36.06. So that's about right here, right? And then 30.9 something was like right here-ish, right? Well, no, about 31. I messed that up, sorry. About 31 was, yeah, right about here. All right, so there's 1 deviation below the mean, there's 1 deviation above. Everybody in here, every copy in here is within 1 standard deviation of the mean. What they want you to do is find the probability that it's within 1. So it's easier to use the table in this case. I just want to add up all my probabilities. These are the individual probabilities for each bar Well, I want all of them. So I got to add all those up. 0.091 plus 0.136 plus 0.152, blah, blah, blah. Add all those up. And I did it ahead of time just to save time. It comes out to be 0.758. All right, so what percent? 75.8% of the copies are within one standard deviation, of the mean. Now, I went slow there to give you an explanation. I'm going to go a little quicker now as we move through. So this just shows you a typical normal distribution is bell-shaped or mound-shaped. Example 2, and we're not going to do all the examples in the video. We're going to save some for class, the calculator ones, and then there's some with a table that the table is attached to your lesson, but we're going to do those in class as well. Example 2 is going to go quick. Consider the following data distributions. We talked about normal, right? Normal or a mound shape before. Now, instead of saying mound shape, we're going to call it normal. That's the word we want to use. So they're never going to say mound shaped on the exam. They're going to say normal. We were using mound shape just to describe the shape, but now anytime you see mound shaped, you got to understand that is a normal, approximately normal, we say it is. All right, so which of these are mound shaped? Well, this one here. So we'd say this one is approximately normal. Talking about this one here. We'd say this one here is approximately normal. That one there. This one here is not. This is skewed. This is skewed to the right. And this is neither. It's not mound-shaped bell. It's kind of flat, actually. They call it a flat pattern, but we're not even going to really be studying these, but this is neither, because it just says to classify it as approximately normal, skewed, or neither, so that won't be neither. All right, so on to example 3. I think we understand that. From a distribution with a mean of 70 and deviation of 10, restate each in terms of the number of standard deviations from the mean. All right, so if the mean is 70, so that's our middle. I'm going to draw a little picture here. Get in the habit of drawing pictures. If the mean is 70, that's right in the middle. Where would 80 be? Okay, well, 80 is above the mean, obviously, right? Well, if the deviation is 10, then that means that 80 is 10 above, right? 80 is 10 above the mean. So since the deviation's 10, that's one deviation above the mean. This is a 0 value, and this is plus 1 deviation. The deviation is 10. Each deviation is worth 10. So one deviation, 80, would be 10, would be above. So this one we'd say is 1. We describe this as 1 standard deviation above the mean. That's how we would describe this. It says describe it in how many deviations above the mean, or above or below the mean. How about 50? Well, 50 is below the mean. 50 is over here, right? Well, 50 is 20 below the mean. Each deviation is 10, so you had to go 10 and 10, right? So you had to go 2 deviations. That's 2 standard, I'm going to abbreviate, 2 standard deviations below the mean. Okay, below the mean. How about 75? Well, 75 is above, obviously. 75 is right here. And it's not a full deviation. It's halfway to 80. 80 was a full deviation, 1 deviation. So 75 is halfway there, right? So we'd call that 0.5 standard deviations, a half, right? It's a half of a deviation. Half of a standard deviation above the mean. Okay? Half a standard deviation above the mean. And how about between 65 and 90? I'll just draw a new one because we're getting ugly here, right? Well, 70 is right here. 65 is right here. 90 is up here. Okay? So this was the mean. 65 is a half below the mean because it's only 5 below. So it's 0.5, so we'd say from 0.5 standard deviations below the mean to how many above? Well, 90 is 20 above the mean, so that's going to be 2 deviations. Each deviation is 10. So 2 standard deviations above the mean. So it's from a half a standard deviation below the mean to 2 standard deviations above the mean. All right, that's our window there. Z-scores, and this is going to be our last thing we talk about in the video, Z-scores. The Z-score, its definition, a Z-score is going to tell you what we just did right there. How many deviations from the mean you are. A positive Z-score is above the mean, a negative Z-score is below the mean. So a positive Z-score of 1 means you are 1 deviation above the mean. A positive Z-score of 2 means that score is 2 deviations above the mean. Okay? Negative 3 is 3 deviations below the mean. And that's what we're going to look at here. So example 4 does it for us. Here's the formula to do Z-scores. I'm just going to give it to you and then we're going to use it. Here's our formula for Z-scores. You just take the value you want to find the Z-score of, subtract the mean, and then divide by the deviation. They got to give you all the information. So what is a Z-score of our printer? Well, let's see. The prices of printers in a store have a mean of 240, a deviation of 50. The printer you want to buy is 340. Now you can tell that it's above the mean. The mean's 240, 340 is above. So we know we're going to get a positive Z-score here. So we're going to do 340 minus 240. That's the value minus the mean, divide by the deviation, divide by 50. And that comes out to be, I did it ahead of time again just to save time on the video for you, so we're not going crazy here. That comes out to be 100, well, you can do it in our head, 100 divided by 50, which is 2, right? So our Z equals 2. So how many standard deviations above the mean was your printer? Well, that's exactly what a Z-score is. 2 standard deviations, I'm just abbreviating, above the mean. Okay? So now, last example here for our video, because our last few examples are going to be together in class. So Ashish's height is 63 inches. The mean is 68.1, and the standard deviation is 2.8 of boys' heights. What is the Z-score for Ashish's height? Well, his height was 63. We have to compare that to the mean. The mean is 68.1, so subtract 68.1 and then divide by the deviation. That's the Z-score. All right, it's negative 1.82. If you calculate this, you get negative 1.82. So what is the meaning of that value? What does this mean? You got to not be able to get a Z-score, but understand what a Z-score is. Well, a Z-score tells you how many standard deviations you are away from the mean. If it's negative, you are below the mean. You could tell that anyways. If you're 63 inches and the average is 68, you're below the average, right? You're below the mean. So Ashish's height is 1.82 standard deviations below the average. We'll call it the mean, right? So he has 1.82 standard deviations below the average. So almost 2 deviations below. Now that should make sense because each deviation is about 3, right? About 3, 2.8. And he's what below? He's 5 below, right? He's 68, he's 63. He's 5 inches below. So he's about 2 deviations below. Almost 2 deviations below. Not quite, right? The deviation is about 3. He's not 6 below. He's 5 below, all right? So he's almost 2 of those deviations below the mean. And that's kind of what a Z-score is. It tells you how far away from the mean you are. Okay? And we're going to talk more about, we're going to use those Z-scores, and we're going to be able to find the Z-scores a little easier. Well, not find them easier, but use them to find the probabilities from a table and on our calculator when we get to class tomorrow. See you then.